Hi, everybody. Welcome to Simplify and Scale Data Engineering Pipelines with Delta Lake. My name is Denny Lee. I'm a developer advocate here at Databricks. I want to let you know that we're also live streaming this on our Databricks YouTube channel. So you can go to dbricks.co slash YouTube here. So if you want to go listen to this live stream, if you have to jump off a little bit early, or if you want to listen to it a little bit later on today. This and other of these Delta Lake online tech talks are going to be available at the Databricks YouTube channel. Allow me to introduce myself a little bit before we dive into it. My name is Denny Lee, as noted. I'm a developer advocate at Databricks. I'm a hands-on distributed systems and data science engineer with experience in internet scale infrastructure, data platforms, and predictive analytics systems. I used to work at Microsoft and helped build what is currently known as HT Insight. Worked with SQL Server customers, and now been working with Apache Spark since 0.5. So gives you a little background in my data engineering experience. So some quick logistics. This recording and the slides will be available after this tech talk, after this webinar. Like as noted, it'll be actually also posted onto YouTube, so on the Databricks YouTube channel. Since everybody is muted, please put your questions in the Q&A panel, not in the chat panel. I'll be looking for questions inside there, okay? And we will also provide a link to anybody that logged in who saved a spot through Zoom or through the YouTube channel. So that will give you all the information you need. This does include, by the way, any of the notebooks that we're using for this demo. It's actually included in this presentation, the link, but as well, we're going to provide it inside the YouTube channel, okay? So let's get started. So if some of you have been attending some of the previous sessions, we did talk a little bit about the data engineering journey or the data engineering pipeline, okay? So I'm going to do just a quick call out just to provide people context, but if you want to dive deeper into it, we had last week's Delta architecture, introducing basically going beyond Lambda architecture, introducing the Delta architecture. And the previous week, we also had getting data ready for data science with Delta Lake and MLflow, where we discussed a little bit about this. But the quick context here is that if you look at this particular diagram, on the left side, you see the events. It's going into Apache Kafka or some other streaming mechanism, like whether it's Kinesis or Azure Event Hubs or Cosmos DB. Irrelevant of which approach, typically you have to build a Lambda architecture. This Lambda architecture allows you to deal with real-time processing in the top part of it and batch processing at the bottom. The top is an Apache Spark or structured stream that's processing the data from Kafka and then pushing this data into this unified view to the right, the database. And that's what goes for AI reporting. But then that's for what you're constantly streaming per se. Then there's also the batch data, which is to your left here. And the left data basically streams down and gets written continuously into some table that you can do normal batch processing against. To validate this data, you're going to need to actually build a unified view that looks at, does the validation between the streams to the top and the stream to the left, between the processing you're doing in the structure stream and the processing you're doing ultimately that goes into the table. So that way there's a reconciliation process to ensure that the data is actually the same. Once you've got your data written to this table, as it's continuously written there, you're going to run batch processing. This batch processing allows you to reprocess data into yet another table. And it'll get compacted every hour because the size of your files, you have a lot of small files that are generated from the stream. So we're going to go ahead and compact those files together so that way we can ensure better performance. When you basically have too many small files in any distributed system, basically it's going to slow down the performance of the system. It's here where you'll then be able to do updates and merges against that data. And then also if there's any late arriving data, you're able to go ahead and reprocess it at this bottom table, okay? That's right in the middle. Yet another Spark batch process will then take that data from that table, place it into this unified view, so that way you can do your AI reporting, okay? That's what traditionally a Lambda architecture would look like. And the usual question you want to ask is, can this be simplified? Okay. And so this is basically what the data engineer's dream is, right? You want to be able to process data continuously and incrementally as the new data arrives in a cost efficient way without having to choose between batch or streaming. When we created Spark streaming or structured streaming those few years back, the whole premise of us creating data frames, when we called it things like static data frames versus dynamic data frames, was that you didn't actually have to think of a difference between how to deal with low latency data and batch data, right? In other words, you would treat and run the queries exactly the same, whether you were running it against a streaming data set or running it against a batch data set, okay? So that's what you really want to do. So that way, it's the same, APIs or the same SQL syntax that you're applying, whether it is a streaming data set or a batch data set. That would significantly simplify not just the maintenance of the code, but just as important, the type of thinking that's involved, that you mentally don't actually have to change your thought process just because you're doing things for batch or streaming. And so that dream then basically is on the left side, your Kafka, Kinesis, Event Hub, your data lake. Doesn't matter if it's a streaming source or a batch source. It doesn't matter. Spark takes it, props it into some store, right? And this is where Delta Lake gets involved. Just a little hint there. And then Spark processes it again, and then you have your AI reporting. So that's what you want to do. So what's missing though, in order to be able to do this? Right now, the thing is that Spark is pretty close to solving all of these problems, but you're going like, but there's a bunch of things that are missing to be able to actually achieve this goal. Okay, so let's talk about those, the issues here. The first one is the ability to read consistent data while data is being written. This, as noted in some of our previous sessions, we were really talking about this concept of ACID transactions. Okay, so ACID, back to this concept, is atomicity, consistency, isolation, and durability. That's what ACID stands for. And this concept of transactions is that you want to be able to trust the idea that when data is written to the store or to the disk or whatever it is being written to, you are sure that it actually happened, right? And there is no chance of corruption, right? If you look at traditional distributed systems, when you write them to disk, whether it's Azure Blob Storage or ADLS or Google Storage or S3, it's the same concept. These are base in comparison to ACID. So there's a chemistry joke inside here, but the concept of base here is actually basically available, soft state, eventually consistent. And the most important aspect here is that eventually consistent. And what that means is that, traditionally, when we have these cloud storage, or even with the Hadoop system, there's by default, there are 3 copies of the data written to disk or written to storage. So the idea is that potentially client 1 hits node 1 and client 2 hits node 2 of this, basically the 3 copies of the data. Well, eventually consistent in this environment basically means that I've written the data to node 1, but I haven't written to node 2 yet because there's some delay. But it's possible that client 1 and client 2 hit node 1, node 2 at exactly the same time. So for client 1 that hits node 1, they'll see the data. For client 2 that hits node 2, they don't see the data. All right, this is this concept of eventual consistency, right? You're not consistent in whether the data exists or not. Okay, well, this is important. This concept of consistency is extremely important if you want to be able to look at streaming and batch data concurrently, right? Because if you're streaming data and you're constantly writing to disk extremely quickly with all these small files, right? The distributed storage that you're writing to, whether it's on-prem Hadoop, whether it's your own environment, whether it's cloud storage, doesn't really matter. There's multiple copies of that data sitting somewhere else. And again, back to the example I used, client 1 is hitting node 1 and client 2 is hitting node 2, and client 1 sees that data and client 2 does not see the data, those clients are about to perform some action against the data in which you've got inconsistent data. So for example, if I've tried to do an update or delete or something else, client one sees it, client two does not see it, their actions are going to be quite different, or the results of those actions are going to be quite different, right? So this ability to have consistent data, right, is extremely important, right? The second call out, ability to read incrementally from large tables with good throughput. That's a super important concept, right? The larger the table, the more resources it takes. You want to actually have some mechanism to have consistent processing of that data, okay? You want to have that ability to roll back in case of bad writes. You know, for example, I write the data, attempt to write the disk. There are, let's just say, 5 tasks that have to write it as part of this one job. The fourth or the fifth task fails. All right. What happens normally in this case? Well, the other 3 and possibly the fifth one will write to disk, and the fourth one will roll back and fail. Well, what happens is that means 4 of the 5 tasks have written to storage, right? While the fourth one, like one of the 5, ends up actually not being able to write it. Okay, so it fails writing. So you get the error, except now your data is left in a bad state, right? So in other words, you're not sure what changes just happened to your data, and that's already bad enough if you're just inserting data, right? Because if you're just inserting data, maybe you can just say, oh, okay, I built a checkpoint, or I built a queue. I know that I ran this by this batch ID, or at this particular time, just roll everything back, delete everything manually myself. And that's cool, right? But it gets a little bit more complicated, especially, first of all, it's already a pain just to do that maintenance. But even if you had no problem doing it, running the updates or running the deletes against that data, well, once you've done that and somewhere halfway through the system it breaks, how do I roll back that update? How do I roll back that delete? Right? So you want that ability to roll back. So in case there is an error, whether it's error at the disk level or error in the source system or the business logic, doesn't matter where the error is, but in case there's a bad write of some type, you're able to roll back. You also want to be able to replay historical data along with new data that arrives. So in other words, take all the historical data and also, in other words, have a single table per se that actually looks at both the new data that's coming in as it's coming in and replay historical data at the exact same time. So again, you as the data engineer are looking at data from the standpoint of, here's all of my data at the point of the query, whether it's brand new or old, as opposed to, okay, let me take the new data, let me take the old data, let me go merge them together, let me go ahead and run a query against that. And just as important with all those concepts that we're talking about, the ability to handle late arriving data without actually having to delay downstream processing. Okay. So what's the answer to this? The answer really basically is combining this concept of structured streaming and Delta Lake together in order to create this Delta architecture. We talked a lot about this last week, but as we noted, this session is about simplify and scale data engineering pipelines. So I just want to provide this real quick context first before we dove into how do we do that, okay? But the real call out here is basically unify batch and streaming with a continuous data flow, infinite retention to replay, reprocess historical events as they're needed. And you can actually have independent elastic compute and storage. They can scale independently from each other. So that way you can balance costs, right? That's actually how we want to do this. So let's try this concept all with Delta Lake instead, right? So what we implied with the data engineering journey is basically broken out in this concept of bronze, silver, gold data quality levels, okay? So when you look at the data engineering pipeline, we actually showed like one database icon, but really it's broken down into different data quality levels. Now, some people are going to ask the question, do I actually need to have 3 separate tables? Are these 3 physical implementations? And the quick answer is that in some cases, yes, in some cases, no. It depends on the cleanliness of your source data. If you had already processed and cleansed data upstream, you probably don't need these 3 levels. You probably can just go right to gold. But if you're taking the raw data source where you do need to ingest and keep the data because the REST API that you're calling from is actually non-persistent. In other words, it only holds the data for a short time. Like Kafka will, let's just say you set up your Kafka Kinesis or Event Hubs to only hold data for about a day or for a few hours. You need somewhere to have that data sit, right? So that's what this concept of a bronze table is. It's the raw ingestion. Make sure you have a source where that data resides. All right, then you go to this concept of silver. Now that you're ensure that you've written the data to storage, to disk, right? Let me go ahead and filter it, right? I don't need all these login calls or these IP traces or whatever else, right? Clean it. So in other words, there's data that actually has with simple business logic, I have to remove this description, or I have to change this ID, or I want to filter out all from this particular geo region, right? This cleansing concept, right? So that's what silver data does. Oh, and also augmented. So in other words, if I have other sources of data that I want to join with this data, this is where you would normally do that. And then finally, you're at the gold level. The gold level is basically now that I've filtered, cleansed it, and augmented it, I also will possibly aggregate it as well, right? So in other words, I don't need to look at the 8 million transactions that just happen per hour. I can look at them by minute, right? As opposed to pi second, using that as an example, right? Because I only need minute latency for the purpose of my reporting. So if I only need minute latency for purposes of reporting, I can shrink that hour into I can shrink the minutes down to hours. Yeah, actually, I meant the other way around. I only need hour reporting as opposed to minute reporting. Okay, and so irrelevant of the whatever business logic requires, right? The idea is that this goal table is smaller, more compact, has exactly what you need for your streaming analytics or your AI and reporting to go ahead and piggyback off of. Okay, and so this concept of basically these data quality levels, or the delta architecture, which is what you see in terms of this data quality levels, right? It allows you to incrementally improve the quality of your data until it is ready for consumption. That's the important call out. So if you're a data engineer, I would love to be able to online, be able to just ask you, raise your hands, how many of you are data engineers and how many of you are enterprise data warehousing folks? What does it remind you of? Well, this concept reminds you of basically, okay, your standard data lifecycle. Instead, the bronze table is more like your data lake. You just dump all the data in and you're good to go, right? Then you build a staging database or staging table, right? Which basically allows you to go ahead and filter, cleans, and augment the data. Oops, sorry. And then you build a data mart that actually has those business level aggregates, right? So this concept that we're talking about is very similar, very close to this idea of a data lifecycle. It's just that with the Delta architecture, it's not just a single table in a single database. The idea is that we're talking about different tables applied in a distributed manner in a distributed system. So that's what the architecture is about. And it also allows you to handle both streaming and batch data concurrently. Or so, how do we transition from this traditional data lifecycle to the Delta Lake lifecycle, right? So like we said, raw ingestion. The bronze is this idea of dumping ground of raw data. You often will have a very long retention, errors that often is in the years. You want to avoid error-prone parsing. So in other words, it's really about just storing that data. That's just really the concept of bronze. Okay. As we noted with this silver, right, you've got intermediate data with some cleanup applied. It's queryable for easy debugging. So for example, if you are a data scientist and you want to go ahead and not necessarily work with the business level aggregates, but you want to go one level deeper or more detailed, right, you can potentially just run your analysis on the silver data. This is also common for debugging, right? Because, for example, if I'm I'm just going to use this example. I'm an airline. I have data, and I want to be able to debug or provide customer support for somebody who logged into my website to order a ticket. Right. This is that filtered and cleansed augmented data. It's usually there's enough information inside there so you can debug your way out, and it's all inside here. Okay. And then once you're good to go, you've got business level aggregates, you've got clean data for consumption. It's now ready to read with Spark or Presto. Actually, the star is there. I should have removed the star, but the call out is that as of Delta Lake 0.5.0, we've included the ability to create manifest files. And with those manifest files, both Athena and Presto actually are able to go ahead and read a Delta Lake table as well. So the idea is that Delta Lake is not just for Spark. It certainly started with Spark, and I'm going to show you an example using it, but other systems are absolutely able to make use of Delta Lake because they're able to read the manifest file. Okay. All right. And then as we're sort of noting here, the streams move data through the Delta Lake, whether it's low latency or manually triggered. It eliminates the management of schedules and jobs, right? So I forgot if I included this particular slide in this deck here, but one of the cool examples I like talking about, which was covered in Spark and AI Summit in San Francisco last year, was Comcast. And Comcast went ahead and dropped from 80 jobs down to 3, because even though they were doing a sessionization process that did not necessarily require them to have everything streaming, because they were able to run low latency streaming jobs, they were able to replace all the 80 plus batch jobs and shrink it down to 3 jobs. The combination of ACID transactions of Delta Lake and the able to look at the problem, whether it was streaming or batch in the same manner, allow them to decrease the complexity of their job structure. And they're able to now maintain that system in a much easier way. And so this is an important aspect, right? You know, even if you cannot necessarily take advantage of the streaming per se, because you don't have a streaming job in a traditional sense, you can certainly break it down into small micro batches. So that way you have a job that's consistently running to reduce the complexity of what you're building, right? Now, Delta Lake, in order to be able to provide you all this capacity, now it basically provides you DML, right? The ability to do insert, updates, deletes, merges, overwrites. Now, you can certainly do inserts in gold and do overwrites in bronze. So this isn't necessarily meant as a catch-all, right? It's just simply stating that traditionally in a bronze level, you're either inserting, updating data. Traditionally in silver, you're deleting data so you can shrink it down. And traditionally in golds, at this point, you're merging or overwriting data. But those DMLs, those data manipulation language, those statements can actually be applied all throughout, right? It allows you to do retention, it allows you to do corrections, and it also even allows for GDPR, general data privacy regulations. And this is actually an important concept within newer systems, where if you're holding a lot of data, CCPA and GDPR, these concepts of GRC or governance, risk and compliance, risk management compliance, it's an important aspect of how to ensure your data is not just safe, but you ensure the privacy of the individuals behind that data. And so that's an important aspect, which actually we're going to cover next week, by the way. So in next week's session, Tech Talk, we are going to be talking about how to address GDPR CCPA by utilizing Delta Lake. So please do join us next week for that session as well. So a little shout out to that session, okay? But with Delta Lake, the concept is that, you know, I can run, if I need to recompute, if the business logic changed, right? I can clear the silver, I can clear the gold, I could just run deletes, and then I can restart the streams or reprocess the data. I could scale the environment or scale the systems to go ahead and process more data, and then you're good to go, okay? And so now let's talk about demos. The remaining 20 minutes or so, 25 minutes are purely demo. So now that you've been patient enough to let me give you some of the context, let's go right into the demo product, okay? All right, so, all right. So like I noted, this notebook actually is available for you to download and use. I'm actually only going to be using a small portion of it, but just to sort of give you some context about how to build these scalable pipelines, okay? So I'm going to stick to just streaming and processing it, okay? That's all I'm actually going to go do, all right? All right, so this notebook is currently running in Databricks Community Edition. And because it's because we're doing it here, sorry. There we go, that's better. It actually, the data set's actually in Databricks datasets, but you can actually run this yourself as in a Jupyter Notebook if you wanted to. And the data set actually, we include a link here on where you get the data. Okay, so you can certainly go run this data on your own environment. You do not actually have to run this on Databricks. But if you do, you can run this on Databricks Community Edition and it's free, okay? So, all right, so right now what we have, I just want to start off, we've got some data and it has a schema like this. So you have a loan ID, a funded amount, a paid amount, and address state. This is a loan data that we downloaded from Kaggle. Like I said, we included the link there, all right? And so how many records does it have? Right now, this particular one has only 14,000 rows inside there. So it'll be important to call this out later, but that's a quick important call here, okay? So I'm gonna go ahead and run this particular function here, okay? Go ahead and refresh. All right, there we go. Okay, I'm going to run this function. Now, I'm not going to dive too deep into it, but the whole point here is that I'm actually going to create this generate and append data stream. The purpose of the stream is basically I'm going to take data that was based off of the loan data that I have, but I'm going to insert this into the same location, but I'm going to do it in Parquet. Okay, so originally near the top here, I'm just going to scroll back here just to give you some concept. I created this Parquet path. So basically I created this particular folder. So my table, this loans Parquet table, is based off of the data that's residing inside here, this temp SAS EU19 demo loans, okay? So I'm going to go ahead and run this generate function, right, which basically does that, okay? Generate and append data stream. It's going to put data into that Parquet location, all right? So now when I run it, basically a structured streaming job is going to kick off. So we're going to wait a few seconds for it to kick off, all right? And so here we go. So we're going to initialize the stream. And what's happening here is that the reason I'm showing this in Databricks Community Edition is that it has this cool little thing where I'm actually able to show you the input processing rate and batch duration in terms of, okay, we're processing about 20.6 records per second. So we're putting data in, okay? So far, so good, all right? So let's see if any data is being added into it. So I'm gonna go ahead and just run a quick count against that same Parquet path or where that loans Parquet table is, all right? So I'm just gonna run it directly off of here. And when I run this, you'll notice that there's 170 rows inside here, okay? That number seems a little off and I'll talk to you about that in a second, but what happens if I try to run a second stream? Right. And so this is an important aspect of if I'm trying to go ahead and scale my data engineering pipelines, right? I've got more than one source kicking in. Sorry, I hope you did not hear me sneeze. My apologies for that. So I have more than one source because it's a distributed, multiple REST APIs or distributed source or whatever, right? And so I want to run a second stream to go to that exact same table. What happens if I try to do that against a Parquet table, okay? So it's going to kick in. It's going to try to start writing to that same location, all right? Except what you'll notice is that, sure, the batch duration is almost a second, but there's 0 records per second, okay? And so that is nothing's going in, all right? So this second stream can't write to the first, write to the same location as the first stream. So data is still going in from the first stream, right? It did jump up to 570, as you can tell from here, right? So data is still going in, as you'll notice from this one, but it's not going in here. Right? It's just not happening. And why is that happening? Because ultimately what's happening is that when you're writing data to disk, right? There is no concept of this ACID transactions where every single write is protected and there's a transaction around it protecting this information. What's actually happening is just it's in essence, there's a lock if you want to think of traditional EDW, or in essence, there's a lock to the table. It's writing to disk. So the first stream's able to do it, but the second stream just can't do it. Right? So so you can't, what ends up happening more times than not, you end up creating multiple tables and then you have to merge those tables together, i.e. increase the operational complexity of your system. But wait, remember how I started off, I said there were 14,705 rows, right? And right now there's certainly less than that. I mean, I'm streaming data in, so it's probably a little higher now. So we'll just run it at 870, but certainly not the 14,705 that we talked about, right? So if I look at the data, and look at it, you'll notice that in addition to loan ID, funded amount, paid amount, and address date, I also have timestamp and value inside here. Okay, so the schema changed, right? Well, that's our problem here, Okay, so I'm going to stop the streams as I explain this concept. Okay, what's basically happening is that because we had the streaming query, one of them, because the second one didn't work, right into Parquet table. Because it's a structured streaming job, automatically structured streaming jobs, we include the additional column of timestamp and value. So for example, if I go back and look at the code here, right? So I'll just open up here, right? My stream data is actually right here, right? So I'm reading this data. I'm asking for the loan ID, funded amount, paid amount, and address state, okay? I did go ahead and do a write stream, right? Which is basically, you'll notice that it's stream data dot write stream, format, table format. That was one of the input parameters, which was Parquet, okay? The option is the checkpoint location. It's just a location so we can ensure that our stream runs correctly. So we can skip that for now. We do a dot trigger, which is every 10 seconds, we're gonna go process the data, i.e. go write the data. And then basically it goes into that table path. That table path is the same Parquet path that we had listed originally, right? So that's great. You'll notice that I never actually specified timestamp and value. So it was automatically added as part of the streaming process, okay? So because I actually automatically added these columns, this timestamp and value, what happened is that I have two different schemas. I have one schema, which is the old one that only has 4 columns. And then we have a new schema with 6 columns. And so because I have 6 columns, in essence, I basically overwrote my original table, okay? So that's why when I'm querying the data, I'm only seeing the 850 or the less than 1,000. I'm not seeing my original 14,000, okay? So this is a problem with Parquet, all right? There's this no concept of schema enforcement to ensure that the data actually coming in is actually going to be the schema that's already existing inside the table. And you can't, there's no interoperability between not just batch and streaming workloads. I can't actually even have 2 streaming workloads writing to the same table concurrently, right? Which sort of sucks, okay? So let me just restart this process over again. I'm just going to go ahead and clear out the data, and I'm going to republish the data. So I'm just going to run that process. And once this is finished, I'm going to go ahead and run this step, which is to basically create this as a delta table. So in other words, here's the original Parquet file, Parquet file that we have here, okay? I'm going to go ahead and run this. Now, instead of the Parquet path, I'm going to go ahead and do it as a delta path, okay? So I'm going to go ahead and store this as a delta table, okay? That's what this line is, okay? Right here, okay? So as you can tell, it's pretty easy to switch from Parquet to Delta, right? In other words, I read from Parquet, and then I write with Delta. So exact same format, right? Read.format Parquet, write.format Delta. If I want to read a Delta table, it'll be read.format Delta, right? Pretty straightforward, okay? So now I've created this Delta table. I also happen to create a temporary view as well, just in case, all right? So let's see the data one more time. Okay, and we should back to 14.705 as you see here. And we want to look at the schema real quick. All right, so the schema is in fact 4 tables. Oh, sorry, 4 columns, I'm sorry. All right, so I'm back to where I used to be now, but the only difference is that I've got a delta table as opposed to a Parquet table. And one thing I'm going to go do is that I'm also going to create a loans delta stream. Okay, so I have a loans delta table, which is for batch queries. I'm also going to create a loan delta stream, which is for streaming queries, but they both go to the exact same location, this delta path, okay? So it's the same file system, whether I'm running a batch query or if I'm running a streaming query, same thing, okay? All right, so now that I've got that, okay, so this is giving my quick count, woohoo, 14.705, let's go ahead and try to run this query again. All right, so same one again, all right? But remember, I actually had 6 columns, not 4 columns, okay? So with this one, I have 6 columns, not 4 columns, but guess what? Because I'm using a delta table, I'm seeing a schema mismatch now, right? It tells you right here, all right? If I want to merge the schemas together, I can use dot option merge schemas true. So in other words, if I wanted those additional columns to be included, all I had to do was change the code that I was using to include that option, and I could have allow those 6 columns, sorry, the 2 additional columns to go into my data. But I don't right for now want to do that, but it's a good call out. So in other words, if I have good business justification or good business reasons to do so, there you go. But it's calling you out right here. Here's your table schema, these 4 columns: loan ID, funded amount, paid amount, address, date. And here's my current data schema, right? I've got the timestamp and value. So it's warning me that there's a problem here. All right. So let's instead just simply go fix this. Okay. All right. So in this case, what I'm doing is that the stream data, because I know the stream data automatically includes the timestamp and value because it's streaming, let me just go ahead and specifically specify .select where I'm only going to include the 4 columns. Now that I've only done that, when I write this data down to my delta path location, it'll only write it with 4 columns, not 6, okay? So that's a great thing about Delta Lake, because there's both this concept of schema enforcement, i.e. we prevent data from going in to potentially corrupt the data that you have. And also we allow schema evolution. So if you have a good reason that you want to change over time, we can merge the new schema. For sake of argument, if you wanted to include timestamp value, we can merge the new schema with the old schema, but it won't corrupt the data. The old schema will still be there. Okay, so that's what's pretty cool. All right, so now let's go ahead and run this. It'll take a couple seconds for it to kick in, but so now we have the streaming query kick in. All right. So let's go ahead and kick this off. All right, boom. So now we have a dashboard. It's trying to process records. So now it's trying to put data inside it. It's right now running about 54 or 55 records per second. Okay, which is cool. All right, let's go back up here. And you'll notice right away the number changed, 15255, okay? And over time, as that stream is kicking in, it'll be able to put more data in, okay? Obviously, it'll increase. But what's also cool about it is that because I'm using a Delta Lake table, I'm actually able to go ahead and run this again, all right? So in other words, I have a second stream, right? So this is my stream query 3. Same concept, same code. I'm just going to be running it. For sake of argument, this would be representative of 2 different sources, but they have the same schema, same data that are all trying to write to this thing at the same time. And sure enough, right away, stream query 3 is jumping up to 147 records per second. And if you go back up, you'll notice the numbers keep on steadily increasing here, okay? So this is what we mean by simplifying what you've created. Okay, simplifying your data engineering pipelines. The fact is that irrelevant of a single source, multiple sources, whatever, if I decide that I need to put everything down into a single table, which is what this example is, I can't, because I have multiple streaming jobs that can hit the table concurrently. And because I have asset transactions, I'm protecting the data underneath this the entire time. All right, and let's go ahead and run this. Remember I said that we were looking at loans underscore delta underscore read stream. That's actually telling you what the read stream looks like. But I can also look at the batch, all right? So in other words, the loans underscore delta. Remember, this is a batch table that's looking at the exact same source, right? And again, now I have a batch query read, which is telling me right now it's 23,455. I've got 2 streaming writes, all happening at the same time, right? So this is how powerful it is, right? That you can actually, because I can have multiple streams, read and write, multiple batches, read and write, now I can actually simplify everything because everything's shoved into a single table, right? I can then organize my jobs to be streaming jobs as opposed to just a bunch of batch jobs. Instead of having 20 batch jobs, I can potentially run a single micro batch or streaming job to actually simplify things, okay? So let's take a look at the file system underneath the covers, right? Remember, like I said, we're going to stop all the streams, right? And then let's take a look at it. And so this is the delta path that we were talking about before, right? What you'll have here is basically, if you'll notice, it'll be just a bunch of Parquet files, all right? So here we go. All right, so same thing as you're used to working with Parquet. The main difference is there's this delta log folder, okay? Otherwise, that all the original Parquet. These little small Parquet files are from the stream, and you probably can see this big one, larger one. That's the original Parquet file that had the original data. All right. So if you look at the log, what is the log? Basically, it's it's showing you all the different versions of the data. So every single insertion has a JSON around it. That JSON describes and tells you exactly what happens inside that transaction. Sort of cool that way, okay? In fact, let me go ahead and just choose this one for the fun of it. You open up the JSON file and take a look at it. So it tells you the timestamp, the commit information, who it was that did it. For example, that's me. What type of information, like it was a streaming update, and all the transactions, right? This is a transaction that happened, and all the values associated with that. Okay, all that's stuffed inside here. That's actually what's inside that JSON. Right. So underneath the covers, we're creating this ACID transaction to basically protect the data underneath the covers. Okay. And actually, to make it look nicer, we actually create this history. So you just go describe history, and then you see all the versions of the data. So all the streaming versions, all of it right here. Okay. All right. So before I jump into any more of this, let me go back to the slides real quick. Okay. So let me do that. Oops, sorry. There we go. All right. Okay. So let's connect those dots back together. Okay, since we've got about 7 minutes left for the presentation, I still want to leave some time for Q&A. Let me connect the dots, right? Am I able to read consistent data? With Delta Lake, I am able to because I've got snapshot isolation between the writers and the readers, right? Just as you saw, I was able to go ahead and run multiple stream writes and read all at the same time, right? Am I able to incrementally read from a large table? Yes, I can. Actually, I've optimized file source with scalable metadata handling. Okay, this scalable metadata handling, actually, let me go back and just show you this real quick. Oops, sorry, I gotta get this right. All right, you'll notice that there's this checkpoint parquet here, okay? Okay, so every 10th JSON inside here actually has a dot parquet inside it. All right, so there's a question that just came in asking me, you know, what is that parquet? They managed to know it. So they saw the JSON, but if someone wondering what the parquet. So let me answer that right now. The parquet here basically is to go ahead and say, all right, after every 10th transactions, I'm going to convert this to parquet. So instead of actually trying to read each individual JSON file, I'm just going to Spark will be able to read the parquet file, such that later on, if I shut down the cluster and then I'll relaunch the cluster at a later date, instead of trying to read every single JSON file, I'm just going to read the parquet files. Okay, and so that'll make things a lot easier. It's already in the format that'll stream into memory, and boom, you're up and running. Okay, and so basically, instead of reading 31 JSON files, I'm going to read 3 parquet files, and then I'm actually going to read the one additional JSON to be up to speed on what the current transaction workload is. Okay, all right, perfect. Okay, and so am I able to roll back? Yes, you can. I actually just have this concept of time travel. I don't have time in this today's session to actually go ahead and show you time travel, but if you're looking at the previous YouTube, it's on YouTube right now, excuse me, previous tech talk on getting data ready for data science, we actually show a lot about rollbacks and time travel. This idea that because you're able to see the history of the table, it's not just you see the history, the data of that table still resides there. So that means I can actually roll back to that previous view of the data, which is pretty cool, right? So for example, I can go ahead and roll back to like the 19th version of that data, all right? So for sake of argument, all right, I could do something like, okay, I forgot how to write the version statement. This is what happens when you try to do stuff live. So I'm just gonna, fortunately, I actually have the version statement down here. So I'm just gonna copy it. Oops, sorry. So the good news of what I'm showing here is I'm actually showing you the full notebook. That full notebook actually shows you the rollbacks and everything inside here. So it's pretty cool. But let me go ahead and actually get the time travel correct. Okay, you know what? I probably, with the time left, I'm probably going to skip this, but let me go ahead and actually finish off what I was talking about, and then I'll get back to the demo here. Okay, cool. So back to presenting here. Sorry about that. All right, so we can also replay historical data, right? Stream the backfilled historical data through the same pipeline, which is sort of nice, right? So in other words, whether it's historical data or streaming data, I can actually merge the two concepts together without any problem whatsoever. And this is important because I want to be able to look at the data without any problem whatsoever. I want to be able to look at the data, irrelevant if it's new data or old data. I want to be able to look at it without actually going ahead and saying that I have to build a separate table for streaming and a separate table for batch. No, instead I can just go ahead and look at the same table that has both my batch data and my streaming data at the same time, which is sort of nice, right? So that's an important concept as well, okay? All right, and then also just as important, I wanna be able to stream any late arriving data and add it to the table as they get added, right? This is basically this concept of like, okay, well, I have data that's coming in. When the data is coming in, I want to be able to go ahead and make updates to the data, or I want to be able to do deletes to that data. Well, guess what? With Delta Lake, I'm actually able to do that now because I have ACID transactions protecting this data the entire time. Because I'm able to protect the data without any problem, then sure enough, I'm able to go ahead and, excuse me, I'm able to go ahead and reprocess it. And this goes back to why we talked about that silver, gold, blue, bronze, silver, gold concept, because that way I can go ahead and look at the data, reprocess the data from the original bronze concept and delete it and reprocess it all over again if I had to, okay? All right, so altogether, this allows Delta Lake to basically allow us to put everything together. How we can build this Delta architecture is because Delta Lake allows us to do all of these things to allow us to simplify our data engineering pipeline. So some quick questions. Who's using Delta Lake? All right, there's tons of organizations, tons of customers. Last night, there's actually 2 exabytes processed, not 1, 2 exabytes processed in last month just alone, right? So I talked about the Comcast Universal case. There are many other customer scenarios that you can check out on the Spark and AI Summit, which actually has that information, okay? Oh, here we go. I did include the slide. So for example, the Comcast was sessionization with Delta Lake. The petascale jobs because they had in order to improve the reliability, they had these petascale jobs that they need to make more reliable by using Delta Lake. Not only did they get the 84 jobs down to 3, okay, they also have the data latency, and just as important, if not more important, they actually had 10x lower compute. Instead of 640 instances, they were able to knock it down to 64, which is pretty cool. All right. All right. So how do you use Delta Lake? Right. To use it, you can basically add a Spark package. You can use Maven, and like I said, with data frame, instead of dot format Parquet, just switch to dot format Delta, and bam, now you're using Delta. Okay. So you can build your own Delta Lake right now if you want to. All right. And then I actually wanted to just do the time travel trick now that I remember what the versioning. It helps if I actually go ahead and save this. Okay. So, helps if I go Loans Delta. Okay, so this is actually supposed to run against a Delta table. So again, I guess in this case, I screwed it up. So my bad on this one. I'll actually have to give you a different version of the code base in a second when I actually have a chance to go ahead and switch to the API. Looks like the SQL context actually isn't working right now. So my bad on that one. Haha. All right. Nevertheless, okay, we'll go back to the session here. All right, so you want to use this notebook. Well, this notebook actually is relatively straightforward. You just download the notebook at dbricks.co, SAISEU19 Delta. All right, we actually are going to go ahead and put this link inside the the YouTube channel link, and also if anybody who signed up for the session, they'll get to go ahead and log into it. So either way, I think you'll be good to go. So by doing that, then I think you'll be able to go ahead and try it out and give it a run. Okay. All right. I did want to call out some quick other things, right? Delta Lake is, as you can see here, is rapidly becoming a standard for us. Okay. And so because it's rapidly becoming a standard, there's a question here: will it work with Hive? Yes, in fact, we're working with the community right now to go ahead and figure out how to basically, excuse me, how to work with Hive. So this is right now in private preview right now. And so now that it's in private preview, we'll make it into public preview shortly. But the idea is that we'll be able to go ahead and make it available for in Hive to work with. Okay. We can also, give me 1 second here. Like I noted in the Delta Lake 0.50 blog, we're actually going to be able to go ahead and showcase it using with Presto and Athena. We also working with Redshift and also Snowflake. So, and this is just the current numbers right now we have right now. Okay, so we actually will have more shortly. But as you can tell here, there actually is a great number of connectors already able to work with Delta Lake, which is pretty sweet. Okay. Also, Delta Lake providers. Okay, there's partners and providers that are already working with Delta Lake. You can go ahead and actually work, as you can see here, working with Tableau. You can also work with Privacera, Atuni, Talend, StreamSets, Click, Wandisco, Informatica, and in addition to that, Google Dataproc. Okay, Google Dataproc recently made an announcement to actually be able to go ahead and work with Delta Lake as well. We're expecting more and more announcements to come out shortly. So, so basically, take your time, and we're going to go ahead and be able to showcase that. Okay. And then users Delta Lake. This is just a small example of that, but there's a lot of cool examples of customers that are currently using Delta Lake, whether they're using Databricks or they're not using Databricks, doesn't matter, they're all using Delta Lake. So it's a pretty cool thing, right? So saying that, I'm gonna leave a few minutes left to go ahead and answer some questions, but if you want to listen to this session, and you can subscribe today by using dbricks.co YouTube or re-listen, and in between all of that, I did want to go ahead and rerun that demo because I kept on screwing it up. So you notice originally I have, let's see, here we go. At least 23,000 inside my loans delta table. So I'm going to go ahead and run this little code snippet instead. This will say, this is what version 19 looks like. So now I'm going to go run that. Okay. And this is at the 19th version of our stream here. Okay. So right here. So I'm actually down to 22,455. What was it look like when it's version 0? I'm going to run that again. So this is when the table was initially just created the first time, okay? And it's 14,705, right? So this is this concept of time travel that I was talking about. So my apologies for the delay here, but that's more or less the concept, that you're able to run time travel to roll back. Also is very handy for GDPR purposes. And that's also, like I said, a great segue for us to go ahead and talk about next week. We actually have a session on how do you address GDPR and CCPA using Delta Lake. All right, so a few questions left. So let me go ahead and try to answer them. If you do have questions, like I said, place them in the Q&A. The first question I want to answer is, can I use Delta Lake for OLTP workloads? And the quick answer is, it is not designed for OLTP purposes. It's really designed for the purpose of data warehousing or BI type queries, right? The data warehousing data lake workload. If you want to use it for OLTP, I would actually just suggest an actual OLTP system. We're not actually trying to simplify that part of the process. We're trying to simplify the process where you get to analyze the data and go ahead and run machine learning against it, okay? And I believe there was also another question about, can we create this over using Hive? As noted, the Hive connector is currently in private preview. It will become publicly available shortly, all right? And can I use Delta Lake on-premise? That's a great question. And you absolutely can use Delta Lake on-prem, okay? Delta Lake itself actually is basically, for all intents and purposes, just a jar, right? That you add to your Spark process. Okay, so for example, you go dash packages, so you can basically include the jar or include the Maven coordinates, or basically use Maven if you're compiling, or SBT or whatever else. But the point is that once you've done that, now the Delta jar is included. So once it's that, so if you've got an on-premise Spark environment, you absolutely can go do that. Just include the jar, the latest Delta Lake jar that matches your Spark version and your Scala version, and then you're pretty much good to go. Okay. All right. I'm going to finish up with the answer, how likely can we use this in production, right? And the fact is, actually, this project, Delta Lake, has already been in production for the last 2 years, okay? When we originally created Delta, the backstory for Delta was that we were trying to build it to address some of the oops, like as in I made a mistake, errors that people made into their data. Or we're trying to address the issues that we had for streaming. Okay, so because we were running into those issues, we actually built Databricks Delta as originally a Databricks project, which was sort of an add-on to Spark. But due to its popularity, due to all the questions asked, due to everything that people really wanted to see, we realized that this project made a lot of sense, not just for the Spark community, or for that matter, Databricks, but not just for the Spark community, but for the data engineering community as a whole. That's why we open sourced the project last year, actually. So it's an open source project. You can use it on-prem, you can use it for your own environment, EMR, or HD Insight. You just have to make sure everything's matching. Just as long as using the correct versions of Spark, you're lining up the Spark version and the Scala versions, you will be able to use it, okay? Now, saying all this, if you want to learn more about how we got here in terms of like how we can use it in production, things like that, the other thing that I would actually ask you to do is go to dbricks.co YouTube, or our Databricks YouTube channel, and check out the genesis of Delta Lake. This is where I interviewed Brock Yavez, senior engineer, software engineer at Databricks, who actually was part of the creation of this project, right? So you can learn a little bit more about the backstory behind it as well. Okay. All right, well, that's it for today. I realize that there are other questions. I apologize I couldn't get into all of them, but I want to be cognizant of the timing here. So I do thank you for your time, for attending the session. Please do, number one, be patient with me for my mistake. I'm trying to get that particular time travel query done for you, but at least I got it done, so thank goodness for that. Number two, you've got comments. Go ahead and ping me directly at my Twitter handle, @DennyLee, or just as likely, go ahead and go to the Databricks YouTube channel and go ahead and chime in and put your comments on the directly on the YouTube channel. I will regularly log in and answer those questions. And finally, also go to delta.io. That's the Delta Lake page. Okay, so the latest videos, the latest notebooks, tutorials, all of them are actually there. So please go ahead and attend that.